Hello, and welcome again to A Minute with a Molecule. As always, you have 1 minute to look at this slide and to prepare your explanation. When your minute is up, I will share with you an exemplar answer. Today, our molecule of choice is H2O, the water molecule, and here you can see a model of the water molecule. Here, you can see the typical bent or V-shaped molecular geometry of this molecule. The same water molecule is referred to as having a tetrahedral electron domain geometry. When we speak of a molecule's shape or its molecular geometry, we do not give any consideration to these lone pairs of electrons. So here, the water molecule is shown as its typical bent or V-shape. Note the angle here of 104.5 degrees. And that's because when we consider its tetrahedral electron domain geometry, the repulsion between the two lone pairs shown here and shown here on this Lewis structure, that repulsion is greater than the repulsion between the bonding pairs. So what we say is lone pair repulsion is greatest, followed by lone pair to bond pair repulsion, and the least repulsion is between these two bonded pairs. This is where we can get this bond angle of 104.5 degrees, smaller than the typical angle of a perfect tetrahedron, which is 109.5. So that's why we can also say less than 109.5 for this and greater than 109.5 for the lone pair to lone pair repulsion. The water molecule, of course, is well known for its hydrogen bonding. The term hydrogen bonding is an exclusive type of an intermolecular force reserved for fluorine, oxygen, and nitrogen. In our last episode, we featured nitrogen. And today, we look at the electronegativity of oxygen versus hydrogen, and we can see that that electronegativity value between these two is 1.0. Remembering, of course, that electronegativity has no units. It's a relative value. The highest electronegativity in the periodic table is assigned to the fluorine atom. So here, because of this difference in electronegativity, we have polar bonds. Small negative charges at the oxygen and small positive charges at the hydrogens. Overall, of course, the water molecule also has a molecular dipole, with electrons being pulled more in this direction, giving a polar molecule, and the negative sides of these polar molecules attract to the positive sides. Each water molecule bonding to 4 others around it by hydrogen bonding. And this is central to water's life-sustaining properties, such as its high boiling point, its high surface tension, its high latent heat of vaporization. And that's why it's such an excellent molecule for supporting life and resisting changes in temperature and for maintaining homeostasis. Apart from all of those, of course, let's focus on this little aspect down here of the water molecule. And here we can see water ionizing into OH minus and H plus, and we have a positive delta H here, which means that it's an endothermic process. Energy is needed to break up or to ionize this molecule. So with that input of energy and it being an endothermic process, following Le Chatelier's principle, it means that if we were to increase the temperature in this system, then the equilibrium would shift towards the side that absorbs that energy, which is moving it towards the endothermic direction, where energy is taken in from the surroundings and The system is pushed to utilize that energy that you put in. So at high temperatures, we will get this equilibrium going more towards OH minus and H plus, which is why it's important for us to note that the pH of pure water at 298 Kelvin is the negative log to the base 10 of the molar hydrogen ion concentration, and that comes to 7. But if we were to increase the temperature, then the equilibrium would shift and the concentration of both the H plus and the OH minus would rise. So therefore, if water's temperature is increased, what's going to happen is that the concentration of its H plus would go up, and you would have a pH that is lower than 7. That might sound counterintuitive, and I want you to think about it carefully, because if the H plus concentration rises, this -7 would not become -8. It will become -6 possibly, in which case the pH would become 6, and because these two ions must be equal in concentration, then the POH would also become 6. Remember, pH plus POH is equal to 14, but only at 298. At a higher temperature, pH might be 6 and POH might be 6, and the sum might be 12. But that would be at some temperature that's higher than 298 Kelvin. And always remember that water is not becoming acidic because its pH drops below 7. It's faulty to say that water becomes acidic at higher temperatures. Yes, its pH might be 6, but its POH is also 6. And once those two are equal, you will have no acidity, because acidity is attributed to an excess of H plus over OH minus. And same for alkalinity. It's an excess of OH minus over H plus. So this entire discussion here is connected to acids and bases. This discussion here is connected to topic 2 and topic 1 of the chemistry guide for first exams in 2025.